Hello everyone. With the advancement of processor technology and in an attempt to make advancements in the speed up of programming algorithms, a new paradigm has evolved and brought about the parallel programming. To utilize this new paradigm, some companies like AMD, Nvidia, and some universities have even engineered new and custom types of processing units that are parallel focused in order to efficiently utilize parallel programming. The current processing units available are multi-core central processing units or CPUs, graphical processing units or GPUs, and accelerated processing units APUs, which we're gonna talk about today. Ideally, the parallel processing speedup would track with the number of processors used for any given task, and the perfect speedup curve is rarely reached because parallelism entails a certain amount of overhead. The inherent parallelism of the application also plays an important role in the amount of speedup. Some tasks are easily divided into parts that can be processed in parallel. So in those scenarios, speedup will most likely follow a common trajectory. Um, so for today's agenda, we're gonna start by explaining what is an APU. We'll take a look at the Trinity chip from AMD, also the Intel Sandy Bridge, the Intel Ivy Bridge, and we're gonna see some of the important reasons why some of us should consider an APU over other processing units. And we'll finish the presentation with a comparison of an APU, a CPU, and a discrete GPU system. Let's take a look here at the typical GPU plus CPU setup. This is a three-step processes and requires the data transfer through PCI Express interface. Although the computation by GPU is very fast, the limiting factor here for speed up in the performance comes during the large data transfer through the PCI Express. So to remove this bottleneck for data transfer, APU technology comes in. So what is an APU? An APU is basically a microprocessor that combines the processing potentials of both the CPU and the GPU in a single chip or a single die. In most systems, the CPU and the GPU are two separate entities, so there isn't actually a problem with this. Expect that the data transfer rate will drastically improve if the two processors are closer to each other. Furthermore, these two units operating at the same time usually results in a higher power consumption. So in 2011, AMD introduced their first high-performing and power-efficient processor that achieved that by combining the advantages of the CPU and GPU into one single chip, popularly known today as APUs, which can also include video processing and other application-specific accelerators. And it turns out that GPUs are good things besides graphics. So the CPU can offload computing tasks to them. To optimize this operation bottlenecks between the CPU and the GPU had to be removed, and the result being an APU. This is an APU from AMD called the Trinity. As you can see, it is combining the CPU, GPU, and video processing and some other accelerator capabilities in a single die, which provides more power efficient processors that are better able to handle demanding operations such as HD video or media rich internet content and DirectX 11 games. Many of the improvements stem from eliminating the chip-to-chip linkage that adds latency to memory operations and consumes power. Because moving electrons across a chip takes less energy than moving the same electrons between two chips. The co-location of all key elements on one chip also allows the holistic approach to power management of the APU. Various parts of the chip can be powered up or down depending on workloads, and in AMD APUs, a programmable x86 CPU and the vector processing architecture of a GPU are both joined together on a single piece of silicon by a high performance bus. Both have local access to high speed memory. AMD APUs also include a variety of other system elements such as memory controllers, I/O controllers, specialized video decoders, display outputs, and bus interfaces. Let's take a look from an APU made by Intel. This one is called Intel Sandy Bridge. Intel Sandy Bridge processors are distinguished from previous generation Intel processors by featuring all cores, including graphics, all on a single chip. This one is manufactured using Intel 32 nanometer die shrink fabrication process technology, and it features Intel Turbo Boost 2.0 for increased performance on as-needed basis. The graphics and video units at the bottom of the chip take about 20% of total area, and this unit appears to consist mainly of synthesized logic, whereas the CPUs and cache use custom circuits designed to maximize performance. Also, we have a big level 3 cache that covers 20% of the chip. There's a successor to the Intel Sandy Bridge, which is the Intel Ivy Bridge. This one is designed in 22 nanometer, and it has low power computing advancements. It has increased graphic performance and enhanced security capabilities. The speed up of the Ivy Bridge is attributed to the use of 3 gate as compared to the planar gate. We can see that here. A small difference in the design actually makes a big difference in performance. You can see that the planar gate is 18 to 73% slower than the new 3 gate, depending on the operating voltage. So why should we consider APUs instead of a CPU plus a GPU? Well, there are three main key differences or advantages: performance, power efficiency, and the cost. For performance, basically blending a CPU and the GPU in the same chip improves the data transfer rate significantly, since they are now using the same bus and sharing the same resources. APUs also support the OpenCL, Open Computer Language, which is a standard interface for parallel programming, uh, which utilizes the computing power provided by GPUs. With its multi-core CPU and GPU, tasks that require the high processing power of a CPU and the fast image processing of a GPU can take advantage of this setup and have a better performance. Power efficiency. Combining two chips into one does not only save space, but it also saves power. There's a recent release that features low thermal design power. It's the Ryzen Embedded 1102G, which actually features a TDP of only 6 watts. That's drastically less than your conventional CPU or GPU. The cost, with a price tag ranging from around $100 to $400, depending on the features. Purchasing an APU is generally cheaper than buying a CPU and a GPU separately, with similar performance. So basically, you get a better price for the same performance, but also in a smaller form factor and less power consumption, which means less heat. And you have only one component to work with when upgrading in the future or something. Performance comparison. The efficiency of APUs for heterogeneous graph computation is shown in these graphs, and the objective is to compare the performance enhancements using APU. The results shown are based on experiments in which the APU used is based on AMD's Kaveri architecture, which was released in January 2014. The installed discrete GPU provides a comparison point with the integrated GPU and is connected via PCI Express 3.0 bus. The discrete GPU was also equipped with 1 gigabyte of dedicated GDDR5 memory, and the testing machine was installed with the Windows 8.1 64-bit operating system with the AMD Catalyst 14.1 beta device driver, which provides OpenCL support for both the integrated GPU and the discrete GPU. Kernels were developed for the breadth first search or BFS algorithm, which most of us are familiar with, and PageRank algorithm with OpenCL. In BFS, subtasks are executed in an A-level synchronous fashion, which means that only vertices at a fixed distance from the source or the frontier are active in any iteration. In PR or PageRank, by the way, this is an algorithm used by Google Search to rank websites in their search engine. Computations is required at every vertex in each iteration. So in each iteration of PR following utilization, all graph data is read and all algorithmic state is updated. In contrast, the amount of data to be read or written in a BFS iteration is dependent on the degree distribution of vertices in the frontier set. So we can see that the setup with the integrated GPU outperforms the setup with a CPU plus a GPU. So we can safely that this technology is promising for future computation. If you have any questions, please do not hesitate to post them in the discussion sections. And thank you for your attention.